So here we will solve one example problem which is related to the one-way slab. Okay. So a simply supported RCC slab has to be provided for the roof of a room of clear dimensions. So they will give in clear dimensions of 3 meters by 8 meters, and again width of the supporting wall is supporting wall 300 mm. So the weight of the weathering course over the slab is, so weathering course meaning here is floor finish. So the weight of the weathering course over the slab, that is floor finish, is 1 kilonewton per meter square. So take the live load, and live load of 2 kilonewton per meter square over a slab. Design the slab using M20 grade concrete and HYSD bars. So there will be HYSD 415 and 500. So we are considering 415, that is Fe 415 bars. Check the design for stiffness. And again I am repeating the same example once again. A simply supported RCC slab has to be provided for the roof of a clear dimensions 2 meters by 3 meters by 8 meters, comma, width of the supporting wall is 300 mm. The weight of weathering course over the slab is 1 kilonewton per meter square. Take the live load on the slab, that is 2 kilonewton per meter square. Design the slab using M20 grade concrete and HYSD bars. So see here, all these are the given data according to our question. So for this data we are going to design the one-way slab step by step. So this is the data. So our first step is, here they will mention a simply supported RCC slab, but they didn't mention that whether it comes under the one-way slab or two-way slab. So first step is to find out the whether it will be one-way slab or two-way slab. So for that one, so take down the given data as it is, that is our first step. And next step is take down the ratio, so that is Ly by Lx. So see here, the clear dimensions it will be given by 3 meters by 8 meters like this. Okay. So here the shorter span will be 3 meters and it will be 8 meters. So the longer span will be 8 and it will be 3. If you simplify this one, you will get above 2. The value will be above 2, which is greater than 2, that is 2.67. So whenever, already people know the condition, if the longer to shorter span ratio greater than 2, which will comes under the one-way slab. So it will be less than or equal to 2 means that will comes under the two-way slab. Then based on this you can decide the thickness of the slab. So again thickness of the slab. So this is your next step, thickness of slab. So thickness of the slab. So according to Indian standards, for example, the thickness of the slab for two-way slabs, it will be given in the IS also, like some for mild steel it will be L by D ratio will be, span to depth ratio will be some 35 for mild steel, and it will be multiplied by 0.8 for Fe415, means L by D will be equal to some 28. But for one-way slabs, whether it will be simply supported and the span range will be more than, so some this value. So at that time you can safely select the span range will be equal to 25 to 30. So always remember this value. So you can safely select it within this range for this type of simply supported one-way slabs. So based on this you can take the thickness of the slab value, which is D here. So your effective depth, so I am simplifying based on this, your D will be equal to L by 25 to L by 30. So here what is the L value? So L value is clearly given, that is 3 meters here. So that is 3 meters. So I am taking in terms of mm, which is 3000 by 25 to 3000 by 30. So it will goes into 100 times and it will be 120 times. Okay, so the ratio will be in the range of 120 to 100 mm. So you can select the effective depth either 100, 120 or making of the average like 110, 115, whatever the value you can select within this range. But here I am selecting the effective depth is 120. So you can select whatever the range you want. So that is your effective depth. Okay, then fix the overall depth. So what is the meaning here? Effective depth, center of the diabar to the top fiber. Already we people know that what is effective depth. Still there will be clear cover and diameter, remaining diameter bar. So I will show you here, I will explain here that what is that one. See here, so here there will be diameter bars. So your effective depth will be taken from the center of the bar. So from this center, so your effective depth will be taken from the center of the bar to the top. That is your effective depth, which is denoted with D. But here there will be half of the diabar and again the remaining cover. So for that, here we are adopting, so minimum cover for slabs will be 20 and for beams 25, columns 40 and footings 50. So already I explained all these basic concepts in the previous lectures and I uploaded in our channel also. So you please refer that things, you will get easy. So the minimum cover for slab will be 20. It means from the bottom to the diabar, the cover, bottom to the diabar. For example, this is the diabar means, so the remaining thing will be, it will be 20. Up to this diabar, we want to know the effective cover. So effective cover. So here for the main reinforcement, we are assuming, so the diameter bar will be assuming some 10 mm. So 10 mm. So we are using, so suppose we are using some, so this is the trial and error method. That is the reason we are adopting 10 mm diabar. So what is the 10 mm diabar? In this effective depth itself, already taken from the center to the top, it will be 120. And so exactly divided that bar half means you will get in the 10 mm there will be 5 mm bar. So if you want effective cover, you can take from this one. So what is overall depth? Overall depth will be D plus diabar by 2 plus remaining cover. So cover of the bar will be, so for slab will be 20 mm. So diameter we are adopting generally 10 mm. So exactly half means 5 plus here this is the effective depth. This is the effective depth. So this, so this is the effective depth. So this effective depth will be 120. So if you take overall value will be, that one will be equal to 145 mm. Means overall height, thickness of the slab will be equal to 145 mm. So that is the procedure for adopting the thickness of the slab. So first what we are doing means, based on the span to depth ratios, we are fixing the effective depth. So that will be in the range of 25 to 30, whatever the value you can take, it will be according to our convenient. Again, there will be minimum cover in the slab, and again exactly from the center of the bar we will divide. For example, if you are adopting 12 mm bar means you can take here 6. For example, if you are adopting higher bar like some 16 means exactly you will get half of the bar. So like that you can fix the overall depth of the slab, that is 145 mm. Next, our next point is effective span. So already in the question they will mention that clear span. Based on the clear span we will solve the effective span. So what are the conditions for the effective span? So already you people know, while in the concepts also for explaining the beam I showed that effective span is the center to center of supports, and the second point is clear span plus effective depth. So already according to our question, so this is the, and supports also they will given. So the what is the width of the supports they will mention here. So the wall thickness means that is the width of the supports which they will given clearly here. This will be 300 mm. This also in terms of 300 mm, and clear span range will be some 3000 mm. So here it will be taken from here to here. Here also it will be from here to here. So if you want center to center of the supports, so 150 again you will get 3300 mm. So first point will be 3300 mm, and again clear span plus effective depth. So effective depth means center bar to this one. So already we fix according to the span to depth ratio which is 120. So that one will be 120. Again 3000 plus 120. So you will get in terms of 3120 mm. So in this you can consider the value whichever is less, means the effective span will be taken center to center of the supports, again clear span plus effective depth. Out of these two your 3120 is the lesser value, therefore we are fixing effective span will be 3.12 in terms of meter. So that is the procedure for finding the effective span. And again here you remember one more point, if they will mention width of the supports 300 like that, then you can take down this step. Otherwise just find out the effective depth, and again you can take down only second condition, clear span plus effective depth. No need to take this clear span center to center of the supports. Why? Because if they will given what is the width of the support in your example model means, then you can consider according to that in your examination. Otherwise you can just move to this step, clear span plus effective depth, then based on that you can calculate the problem. Then our next step is loads. Then our next step is loads. So what are the loads already given in the question? So that is live load, that is 2 kilonewton per meter square, which is given in our data, and again floor finish which is weathering of the course, that is 1 kilonewton per meter square. So these are the given data. If they are not given means you can consider live load, maybe some range. For residential it will be some 2, and for office purpose it will be some 4 according to the standards. You can take in that range. Floor finish, if you want, if they given means you can consider, otherwise you can take one or else you can leave it, no problem. So there will be live load, but each and everything you can consider dead load of the slab. dead load For example, for beam, slab, all the things you can consider dead load. So what is the procedure for considering the dead load? So I will show you here from this diagram dead load as it is. So dead load of the slab, see here, this is the slab. So dead load means, for example, the slab will be this one. Here what I am telling means B into D into H into its unit weight of RCC. So this is unit weight of RCC, which is given standard, that is 25 kilonewton per meter cube. So the unit weight of RCC will be 25 kilonewton per meter cube. So already we people know this D is the capital D. So which is depth of the, so this is the capital D, that one will be already you people know, which is 0.145. So 145 in mm, but we are considering in terms of meter 0.145. And again, what about this B and H? So here we are calculating the slab for 1 meter. So like this. So already we know that D value. Okay, and again in terms of breadth wise it will be 1 meters, in terms of length wise it will be 1 meter, like this, 1 meter by 1 meter. So therefore I am considering 1 meter, and here also 1 meter. Okay, then if you simplify this one directly you will get 0.145 into 25, 1 into 1, but here it will be meters, here it will be in terms of meters, here it will be in terms of meters. If you simplify this one, whatever the value you can calculate, you will get in terms of kilonewton. That value will be 3.625 in terms of kilonewton. But here we are calculating entire this dead load for meter square, 1 by 1 meter into meter, meters square. Therefore we are considering kilonewton per meter square. If you observe here, you will get that point very clearly. Live load will be given kilonewton per meter square, floor finish will be given kilonewton per meter square. For example, if you see the same thing for the beams, for the beams, I will explain beams here. So dead load for beams will be taken as B into D into, again here also H into its unit weight of RCC. You will get that one will be kilonewton per meter only. Why? Because here the beam will be like this, the beam will be like this. So here overall depth will be known, and again breadth also known. What is B? B value and D values taken some 300 by, or some D value will be equal to some 450, whatever the value. Here it will be 25, and we can take down this H value like some 1 meter. Okay, this H value some 1 meter, and if you cancel this one you will get entire value in terms of kilonewton only. Here meter cube means this meter cube, meter, meter and meter, but overall value will get here is kilonewton, but we are considering only for 1 meter because this is a beam. But for slab both side 1 meter in lengthwise and for widthwise 1 meter. Therefore for slabs you are considering 1 kilonewton per meter square. For beams we are considering just meter. Why? Because already we know breadth and thickness, means depth of that particular beam. So that is the difference what we have to remember for calculating the dead load of the slab and dead load of the beam. So here dead load of the slab will be 3.625 kilonewton per meter square. So you know the difference why here it will be considered in terms of kilonewton per meter square, and for beams it will be kilonewton per meter. And so you take down the total load. So if you want a total load, what can we do? You can add all these things. So total load will be total load. So total load. So after simplification you will get 3.6 and again 3. Maybe the value will be 6.625 kilonewton per meter square. Again factored load. So factor means if already while explaining the concept itself I told you can take for limit state of collapse in the for a concrete it will be 1.5 times of the total load, that is 6.625, means we are taking extra safety factor, that is 1.5 times. So exactly half of the value extra, that one will be equal to 9.9938 kilonewton per meter square. So this is the factored load, total factored load for this slab. Then based on that you can calculate the bending moment. So here I will explain that bending moment. So that is factored bending moment. So already whatever the value you will get in terms of factor only, so therefore bending moment. So bending moment. So we all of know that the formula for the simply supported beam slab, all the things, that mu will be equal to w l square by 8. So therefore your factored load already we know that 9.938, and LE refers to the effective span what we consider, that is 3.12 whole square divided by 8. If you simplify this one, exactly you will get a 12.0 kilonewton meter. So based on your simplification you will get some approximate value 12.1 like that. No problem, whatever the value you will get, please consider that value only, that is 12.09 for me. Okay, then after knowing this step, then move to the next step, which is, so check the condition. So already we consider the thickness of the slab will be equal to some 145 mm and effective depth will be equal to 120. So whether if we taken this as a trial in terms of L by D will be equal to 25 to 30. So whether this range will be correct format or not, we have to check here based on this condition. Therefore we are checking that one. So minimum depth required, minimum depth required. So for that minimum depth, so what is the formula? All, as we all of you know that for M20 grade concrete, for M20 grade concrete and FE 415 mu value. So already in terms of limiting moment I explained all these concepts in the previous lectures only. So that is 0.138 FCK B into D square. So here already we people know that mu value which is 12.09, and again so we are considering that value in terms of mm, and 0.138 FCK will be 20, and here B. So how much B? We are considering all the things for 1 meter only. So here I am taking 1000 in terms of mm and D square. So if you simplify this value, so here you will get a D value. That D value will be exactly 66 to, or in that range 66 to 67 like that range. So see here, so minimum depth required for this slab will be this much. What we provided 120 mm means the minimum depth required for this slab will be 66.22 mm, but we provided 120 mm. So the minimum will be 66.2. For in some cases, for example, we provided some 60 mm like that. So the minimum requirement will be 66.2, means we have to limited this value to up to here. Why? Because here the minimum requirement is 66.2, means we are providing less than that 66.2, means it will be give some cracks or deflection, and you will get so the concept will be wrong. So what if you assume 60 like that, means in the trial section you can limited this value to 66.2, and based on that for this one you have to provide clear cover and again diameter of the bar. Then overall you can limit this one to some overall depth will be some like some 180 mm like that. You can restrict that value to here, but here the minimum requirement is 66.2 and we provided 120, means the our whatever we provided that is higher than the minimum required. So we are safe in the depth. Therefore whatever we are using 120 mm is safe only, no problem. For example, if we are using 60 mm in case of 160 120, so and we, so here at that time you have to change this 60 and again restrict that value to 66.2. based on that you can again go for trial section, or else you can just restricted that value to some 66 and again take down the clear cover and effective cover. Based on that you can design the slab. Why? Because the slab required minimum effective depth of 66.2, but we provided more than that, so no problem, which is safe here. Then go for the tension reinforcement. So after satisfying the condition we will move to the next step, so that is tension reinforcement. Tension reinforcement. So we know that for finding the tension reinforcement, what is the formula? So you please observe the Indian Standard Code Book, which is IS 456. See here in this code book, so the page number will be 96. It is better to wrote down there also. So in the page number 96, so there will be one formula, that is mu equal to 0.87 Fi area of the steel d into 1 minus ast Fi bd by fck. So take down this formula for finding the tension reinforcement. So in the Indian standards 456 2000, page number will be 96. In that I am taking this formula, mu equal to 0.87 Fy area of the steel into d into 1 minus Fy ast by fck b into d. So here it will be d. Okay. So already we people know the value of mu, that is 12.09 into 10 to the power of 6, and again all the values. So this will be Fi will be 415, and here the unknown is area of the steel, and we know the effective depth also, which is 120, and again 1 minus this 415 into again this unknown area of the steel, and again 20. Here we are considering this b value as 1 meter. Already I told you, that is taken as 1000 in terms of mm, and again 120. So if you solve this value by using your calculators, which you will get in terms of quadratic equation, and finally the value of the area of the steel will be equal to 294 mm square. As for my simplification, maybe somebody will get some 293, 290 or 300, which is very nearer value. Based on their simplification, they will get the value, which is 294 mm square. And again, so whatever the area of the steel, here you will get, you can check the condition whether it will satisfy the minimum reinforce or not. So for that purpose we are checking that value according to the Indian standards. So that is minimum reinforcement. So what is the minimum reinforcement required in this slab? So that also in our code book, I'll show you that one also. So the page number will be, so for the minimum reinforcement, the page number is, so see here in your code book the page number will be 48 in our IS4 code book. So that is the class 26.5.2.5 minimum reinforcement. So the minimum reinforce for mild steel will be 0.15% of the total cross sectional area. However, this value can be reduced to 0.12% when high strength deformed bars are used. So we are using high strength deformed bars, HYSD bars. So that is 0.12% of the gross cross sectional area. So that is the value which is given in our code book. So that is in the page number 48 in IS. Okay. So what is the formula for that one, for finding the minimum reinforcement? So that one will be equal to 0.12% of gross cross sectional area, total area, that is total area. That one will be equal to percentage mean divided by 100 into, so what is its b and d? So b will be in terms of 1000 and d will be 145. Okay. So which you will get a 174 mm square. Means the minimum reinforcement required for this slab will be 174 mm square, but according to our requirement you will get 294. So we are using this one. So the minimum only 174 means we are using more than that one. Therefore area of the steel will be greater than area of the steel minimum. So it will be okay according to our condition. For example, after solving this equation based on the bending moment, you will get some 150 mm square, but after solving the according to the cross sectional area you will get 174. Here if your area of the steel will be less than that required, then at that time you have to limit this value to this one. So you have to provide minimum 174 mm square area of the steel in that particular slab. So whatever we are providing according to our condition, it will be higher than this one. So it is in the safe condition only. So like that you have to check according to our Indian standards whether whatever doing it will be in the according to the conditions or not. Then go to the next step, which is spacing. So for beams, what we are doing, we are taking the number of bars n equal to some capital AST by small AST like that. But for these slabs, after knowing the area of the steel, we have to provide spacing of the bars. Spacing of bars. For that one, there will be one formula, that is S will spacing of the bars will be denoted with S, and this one will be small AST by capital AST into 1000. So what about this AST? The AST refers to the whatever the value you will get, that is 294 mm square. And what about this AST? That is pi dia square by 4. Here you can assume that diameter of the bar. So we are talking about the main tension reinforcement. Here I am assuming 10 mm bar. So if the moment is somewhat higher, means you can assume 12 also. Okay, like that you simplify. Here I am assuming 10 dia bar. So pi 10 square by 4 divided by 294 into 1000. So you will get the spacing of 267.1 mm. And again the spacing will be satisfied this two conditions also, maximum spacing according to our IS 3. So I will show you that one also along with the page number 26.33. If you move to the that class, definitely you will get that one, 26.33. See here in this class, the slabs, the horizontal distance between parallel main reinforcement bars shall not be more than 3 times of the effective depth. Okay, shall not be more than 3 times of the effective depth or 300 mm, whichever is smaller. So already we calculated the spacing here, that is, and next condition is shall not be more than 3 times of its effective depth, and the second condition will be 300 mm. So see this condition, 3 times of effective depth, which is 120, the effective depth value, that one will be 360 mm, and third value will be 300 mm. Out of these three, take down the condition whichever is less. So we are providing out of these three, we have to provide minimum whatever the spacing you will get. So if you observe clearly what they will mention, maximum spacing allowed here it will be 360 mm, but it does not greater than 360 mm. And again you have to satisfy the condition 300 mm, and again 267.1 mm. So you can see here where for example this spacing will be higher than this 300 also, then at the time you can limit that value to 300 only. Okay, so we are considering whatever the limit value. For example, 3 times of your effective depth you will get some 250 mm, but here they will mentioning the condition, this spacing in this particular slab it does not exceed 250 mm according to 3D. So for example you will get here 360, no problem. In sometimes you will get based on the effective depth it will be 250 mm, means at that time if you calculate these two values will be higher also, you can limit this value to 250 and provide the spacing of 250 mm, because whichever is lesser, here the spacing does not allow more than the 3D. So like that you have to consider the condition. So finally provide 10 mm bars. So already we are using 10 mm bars for spacing, 10 mm bars at 260 mm center to center. Again here I am limiting to, here the minimum spacing will be 267, so we can't keep the spacing in terms of digit like 267 like that. So therefore I am limiting that value which is lesser value, not approximation to higher value. Don't go to 267 beyond. If you want, here I am mentioning 260, so or else you can take 65 mm also, okay, but don't go beyond that one. But here scaling of 1 mm in small thread like that, therefore limit to any particular easy value which is 260 like that. Okay, then again here we have to build alternate balls of 0.1 L from the face of the support. I will explain while showing the detailing of the reinforcement. Then we are talking about the one way slab. So here distribution reinforcement is also important. Already I told you distribution reinforcement. So here for one way slab, main reinforcement as well as distribution reinforcement. For example, two way slab means whichever the moment higher. Based on the moment we can design any one of the spacing, and you can provide both side that spacing also okay. But here we can provide a distribution reinforcement for the one way slab, that is distribution reinforcement. So area of the steel. So already for the distribution reinforcement, what is the minimum area means, that is 0.12% of gross cross sectional area. Okay. So what is the percentage? Already we calculated that one. That one will be equal to 174 mm square. So that much of the minimum reinforcement will be required in the distribution reinforcement side also. Okay. And again here we have to provide the spacing bars, capital AST by small AST by capital AST into 1000. And what about this capital AST? Already we people know pi d square by 4. And again this AST will be limited to 174. Why? Because we calculated here minimum area of the steel will be 174. And here how much dia you are considering here? For the main reinforcement minimum we are considering 10 mm. But for the distribution reinforcement we are considering 8 mm. Why? Because minimum reinforcement providing the slabs will be 8. Therefore I am taking the starting value, that is 8 mm. Okay. So simplify this one. Pi 8 square by 4 by 174 into 1000, you will get the spacing of 288.8 mm. So again for distribution reinforcement according to our IS, so same as the previous conditions, maximum spacing will be allowed, that will be equal to maximum spacing. So there will be two conditions. For main reinforcement it will be 3 times of D, here it will be 5D, and second condition will be 450. And again what about this 5D? 5 into 120, that one will be equal to 600 mm, and already this value will be 450 mm. So out of these three, whichever is less, out of these three values we can take whichever is lesser value. If you observe means distribution reinforcement, the spacing will be 288 mm. How much reinforcement we are providing? The minimum reinforcement which is required in the distribution reinforcement. So that will be 174. Based on that the spacing will be 288 mm. And here maximum spacing will be allowed up to 600 mm and 450. So we are providing whichever is lesser value according to our Indian standards. What IS will be saying means, so simplify these three, in that whatever is less you can provide that much will be lesser. But here for example you will get the spacing value will be some 650, but according to these conditions you can your maximum spacing does not exceed 600 and 450. In the whichever is less means 450. So even though it will be your value will be 650, you can't go beyond 450. Even though you will get 650 mm spacing allowed in that bar means, then also you can keep spacing as 450 mm according to our IS. But here our obtained value will be 288, which is lesser than these two, so we can provide this 288 spacing. Again you can that value round up to which is near value 280. So I am provide 8 mm bars, 8 mm dia bars at 280 mm center to center. So this is the procedure for finding up to the distribution reinforcement. And again what about the shear? So your next topic is about the shear. So generally we are finding shear reinforcement for the beams, okay, but for slabs, so actually slabs will be shape and shear, and hence this check may be omitted here. So therefore no need to find this shear reinforcement. Why? Because almost slabs are shape in safe in shear. And coming to the deflection, so already we are coming from step by step procedure, and again each and everything according to our IS. So almost our slab will be safe in deflection also. Again I will show you in shortcut what is the procedure for deflection. So check for deflection. So what is the condition for the deflection check means, if you see here according to our code, so the deflection check will be satisfied this value, your L by D provided, your L by D provided will be less than L by D max into L by D maximum. So what is this L by D max? So here if you observe the condition, so what is the L by D value we provided in our slabs? So what is the L by D value? So you can simplify that one. So what is the L by D value? So that value will be equal to 3120. So your L value will be equal to 3120 and effective depth will be equal to 120, which is equal to 26 here, which is equal to 26. And again check the condition. Okay, so the value will be equal to 26 here, 26, and check this condition whether whatever the value obtained higher than this one or not. And what about this L by D maximum? That value will be equal to basic value, that is L by D basic into its modification factor. What is L by D basic we provided? So L by D basic will be provided for simply supported slabs will be 20 into. So what about its modification factor? This modification factor will be calculated by using one curve in your Indian standard, that is I will show you here, which was in the page number 39, I think 39 plus 13 51. See here, if you observe this curve, based on this one you can find out this one. Here you have to find out the percentage tension reinforcement. Based on that you will get FS curve. So percentage tension reinforcement, so where it will be, so the percentage tension reinforcement already we people know the formula. So that is AST 100 by BD. Okay, so PT will be equal to AST into 100 by BD. So already it will be there in your code book also, Indian standards. That is, so what is your area of the steel? So what is your area of the steel? So your so here already we obtained 294 into some 100 by B will be considering some 1000 into. What about D? D is effective depth here, which is 120. So if you simplify this one, definitely you will get the value in terms of 1000 into 120. So that is 0.245. So which is approximately 0.25 percentage. So for calculating this PT there will be one more formula, that is area of 1 bar into 100 by spacing into effective depth. So which is effective depth. So you can calculate either or, so whichever is convenient according to you. And here based on this percentage you will get 0.245. if you observe in the so the 0 point, so here it will be 0 and it will be 0.4, means 0.2 will be approximately here where I am showing the cursor. So 0.455 means in that again I am showing that middle. So like that you will get a percentage tension reinforcement is 0.245. And again you can relate with this curve. For finding this curve there will be one formula, that is Fs equal to 0.58 Fy by area of the cross section of steel required by provided. So generally for beams you will get that value will be somewhat different. So area of the steel required will be some 290, means after providing 3 dia bars of some 10 mm means 3 into pi d square by 4, again you will get some required by provided value will be different. So you can check the ratio of that one and find out here there in the beams. But for slabs Fs will be equal to 0.58 into Fy. Fs curve will be equal to 0.58 into Fy, and 0.58 Fy value will be 415. What about this area of the steel required to that of provided? So already I told you, for beams means it will get similar different values, but for slab we are providing only one value. Whatever the obtained value we are providing area of the steel based on that one only. So therefore you can take down means both required and provided will be 1 and 1 same only, therefore you will get ratio of 1. if you simplify this one, you will get the curve based on that how much you will get the curve will be 240 Newton per mm square. 240 Newton per mm square. So please relate these two. Here I told you this is 0.2 and here in the between 0.3 and again it means 0.4, means 0.25 means again like that, again in that middle. So relate to 240 curve, straightly observe the value which is related to 2.4. So this is the second curve is the 240 curve is here and again related up to exactly, you keep some scale here means exactly you will get the value which is related to 0.245 reinforcement and where it is passing left side. So that is the modification factor. For example, here the curve is touching up to this point means you can take exactly so approximate. So you won't get any exact values like this approximation graphs. So here modification I am considering some 1.5. So maybe some other visuals will get 1.6, small minor changes. So if you relate coincidence means that one will get as 1.5. So if you simplify that exactly you will get 30 and here L by D will be less than 30. So almost all we are doing satisfying each and every criteria step by step. Therefore, it will be in the safe only. So you please take down this formula. L by D provided will be less than L by D max. Again, what is max? Taking the basic value into its modification factor. So therefore, whatever the value we consider, it will be lesser. So therefore, your L by D provided will be less than L by D maximum. Hence, it is safe in deflection. So that is the deflection control is safe here. So this is the way for finding the deflection. So this is your entire problem.